quotient rule. I will also provide detailed example and graphical illustrations to help you understand how these rules are applied in solving real world. So first, let's discuss what is derivative. So the derivative of a function measures the rate at which the function's value changes with respect to the changes in the input. So for example, if we have a function representing the distance of a car over time, the derivative tells us the speed of the car at any specific moment. So we denote the derivative in several ways, but here are the two common ways. We have the common notations. It includes f prime of x, and then we can also use the Leibniz notation. So the Leibniz notation is dx over dy over dx. So both notations mean the same thing. They represent the instantaneous rate of change of y with respect to x. Understanding this concept is fundamental because all the rules of differentiation that follow, like the product and quotient rules, are built upon this definition. So moving on, um, to visualize what derivative is consider a graph of a function. So here we have a graph, right? So it is y is equal to fx. So as you can see, y is equal to fx. At any point on this curve, we can draw a tangent line that touches the curve exactly at that point. The slope of this tangent line is the derivative at the point um f prime of x sub 0. So graphically, if the tangent line slopes upwards, the derivative is positive. So meaning the function is increasing at the point. So if the tangent slopes downwards, the derivative is negative. So if upward, it is positive, and if the slope if the tangent slopes downward, then the derivative is negative, meaning the function is decreasing. If the tangent is horizontal, the derivative is 0, indicating a stationary point. This visual perspective helps us understand that derivatives do not just give numbers. They describe how the function behaves locally around a point. So next is the limit definition of a derivative. So as you can see in the presentation, right, the derivative can be defined rigorously using limits. That's why the formal definition is f prime of x is equal to limit f of x plus h minus f of x. I mean like limit as approaches to 0, then f of x plus h minus f of x over h. So this formula, it calculates the slope of the second line between 2 points, x and x plus h on the function. So as h approaches to 0, as you can see, as it says na limit h approaches to 0, the second line becomes the tangent line at x, giving the exact instantaneous slope. This limit is what allows it is what allows us to move from average rates of change to instantaneous rates of change, which is why it is central to all calculus. Essentially, this formula tells us how to calculate derivatives from the first principles. All right. So next is example using limit definition. So let's apply the limit definition to f of x is equal to x squared to make this more concrete. So step 1, compute f of x plus h. For x squared, this becomes x plus h squared. So subtract f of x from f of x plus h. This gives us x plus h minus f of x is equal to 2xh plus h squared. Then divide the result by h. So this gives us 2xh plus h squared over h is um, less than 2x plus h. Then take the limit as h approaches to 0. As as h approaches to 0, we are left with 2x. Therefore, f prime of x is equal to 2x. This example shows how the derivative measures the slope of at any point x. For instance, at x is equal to 3, the slope of y is equal to x squared is 6. The step-by-step approach demonstrates how limits produce the derivative. So next is we have the product rule. All right. So okay. So um we have now the product rule. Di mo ni ba? So the we have now the example using limit um product rule example. So let's apply the product rule to f of x is equal to x squared plus sin x. So identify u and v, that u is equal to x squared and v is equal to sin x. Then step 2, compute their derivatives. U prime is equal to 2x and v prime is equal to cos x. Apply the product rule. So f prime of x is equal to u prime v plus u v prime is equal to 2x times sine x plus x squared times cos x. So now notice how both functions contribute to the final derivative. The first term comes from the derivative of x squared multiplied by sine x, and the second term comes from x squared multiplied by the derivative of sine x. This demonstrates that the product rule combines the change in both functions accurately. So yeah, this is the example, no? Differentiating a product of two functions. So d over dx is u minus v is equal to u prime v minus u v prime over v squared. So top derivative times bottom minus top times bottom derivative, and then square the bottom or the v. Next is the quotient rule. So when differentiating a quotient of two functions, f of x is equal to ux over vx. We use the quotient rule. The formula is u over v prime minus u prime, or the quantity of u prime times v minus u times v prime over v squared. So this can be remembered. Um, I mean, like, this can be remembered as the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the square of the bottom. The quotient rule ensures we account for the rate of change of both the numerator and denominator correctly. Without it, we would make mistakes when the functions involves divisions. So again, for the quotient rule, consider f of x is equal to x squared divided by sine x. So compute the derivatives again. U prime is equal to 2x and v prime is equal to cos x. As you can see, then apply the quotient rule. So f prime of x is equal to u prime v minus uv prime over v squared. And v squared is equal to um 2x times sine x minus x squared times cos x over sine squared x. So this formula captures the change in both the numerator and denominator. For example, if x increases slightly, the change in x squared and the change in sine x both influence the rate of change of the quotient. and the quotient rule combines these contributions precisely. So, in summary of our discussion, to summarize, the derivatives measures the rate of change of functions and the slope of the tangent line. The product rule allows us to differentiate functions that are multiplied together, and the quotient rule allows us to differentiate functions that are divided. So understanding these rules is crucial for solving real-world problems, whether in physics, engineering, or economics, where rates of change often involve products and quotients of functions. So that concludes my presentation. Thank you very much for listening carefully. I hope this explanation has helped you understand derivatives, the product rule, the quotient rule more clearly. If you have any questions or want me to go over any examples again, I would be happy to answer them. Thank you.